Okay, so welcome to this evening's Cambridge Physics lecture, Cambridge Physics Centre lecture. Good evening, and tonight's talk, as Maria's just said, it's given to us by Claire Barlow. Now, Claire is a senior lecturer in engineering at the University of Cambridge. Before doing that, just a bit of background. We asked her earlier what her A levels were. A levels were maths, physics, and chemistry. And went on to read material science at Cambridge. Really interesting course, actually, well worth looking into. Her specialism is sustainability and engineering, and the focus really is on the end of life of materials and looking at their environmental impact. And tonight's talk she's titled it Plastic Planet. And I think the main thrust is really looking at assessing single-use plastics and whether is an outright ban on single-use plastics a right response. So if you have any questions, we're going to save some questions to have some time at the end of the talk, but I'll be able to field those. So put those onto the Isaac Physics website, and once Claire has actually given the talk, then we'll be able to go, we'll have some time to hand questions over to her. So once again, welcome, Claire.
Good. So thank you very much. I'm going to give a talk on plastic planets. So I'm going to share my screen, and the host has disabled participants' screen sharing. So that's put a stop to that. Could you enable me to share my screen? All right, we'll try again. Very good. Right. So there we go. So this is what I do on my holidays. When I'm allowed to have holidays, I go to nice places. I find nice beaches and I gather up the rubbish on the beach. And here's a little heap of rubbish that I found on a beach in a very remote part of Scotland. So what I'm going to do in this talk is to talk quite generally about plastic and think about what we use plastic for and whether we should be using plastic in that way and whether we should be doing different things with plastic when we've finished its first use. So what happens to plastics at the end of life? And I will come up with a few suggestions about what we should do, but I'll be asking an awful lot of questions as well. So this isn't going to be a tidy talk that tells you all of the possible answers, but I will try to give some ideas about the way in which we could perhaps do things a little bit better in the future. So we use a lot of plastic, and we use it for things like electronics. It would be very difficult to have the current sorts of electronics that we have without plastics. Transport, plastic is lightweight, it doesn't rust, it's fairly cheap, it's easy to make complex shapes, and cars have an awful lot of plastic in them. Construction works, houses, quite a lot of the way in which we do building now really relies very heavily on plastics. And again, it's an awful lot cheaper than what we do with any other materials. And as you get older and bits drop off and you need to get them replaced, then quite a lot of those replacements are plastic. And it's actually quite difficult to do it in any other way than using plastic. So for all of these applications, I would say that plastic is pretty much essential. It's cheap, got a huge range of applications for it. It's lightweight and it's durable. And that's good for these applications, but actually that's causing us problems later on. So for all of these applications, I would say that plastics are the best materials choice. And I've defined best in different ways, but cheapest, easiest to use, and in some cases, the only material that we can use. So plastic, a really useful sort of material. But what's gone wrong? What's gone wrong with our perception of plastic? Plastic is actually rather a dirty word now. And there are people who promote the plastic-free movement. We should get rid of all plastics. And here's a shot of the sorts of things that they want us to use instead. So, cottons, natural materials, wood. Is that really the right reaction? And then we've got this substitute for an envelope. So this is a plastic-free wrapper. Well, it's plastic. They're defining plastic. They're calling plastic something which is just not produced by petrochemicals, but it's plastic. And actually, it's a little bit problematic. So it says 100% compostable, made from potato starch. Well, we'll take a look at that a little bit later and unpick it a bit. So how green actually is this? So the problem, plastic waste is the major problem here. And this durability of plastic, which is so much an asset in the way that we use it, that means that it hangs about in the environment. And a lot of it gets into the ocean. So in 2017, David Attenborough hosted this Blue Planet 3 series. And it had a huge global impact. And environmentalists all over the world talk about the blue planet effect. So, there was these amazing pictures of marine life, which was getting caught up in plastic, ingesting plastic, really terrible things that the plastic from the marine environment was doing. And people took note. So the general public, even the politicians, started taking note, and things started to happen. They started to happen faster than I would ever expected. And that was going really quite well until the pandemic put quite a lot of things into reverse. So it will come back again. But the Blue Planet effect was a really useful wake-up call, and it's helped to change our attitudes to single-use plastics. So, what is the problem with marine life? What's the plastic in the oceans? Most of it, the big items, are mainly fishing gear, what's called ghost gear, so fishing nets and lines. The smaller items are mainly our domestic rubbish and commercial rubbish, so familiar containers from what we put into our waste. Cigarette filters are quite a surprise there, but they're made of plastic as well. And then there are the microplastics, which are defined as fragments which are less than about 5 millimeters and can get down to very small. So those come from all sorts of sources. Synthetic fibers are quite a big part of them. And there's been stuff in the media about cosmetics with the microbeads. But there's also quite a lot, as plastics break down in the sea and on land, then the particles that comes from that, they're microplastics. And then there's quite a lot also that comes from car tires and road markings. So all sorts of contributors to microplastics. Where does it come from? Most of this marine waste actually comes from Asia, with China being the biggest contributor. And the regions that are producing this waste, they're regions with high population density and very often not very well controlled waste management. And so there can be landfill sites that just aren't controlled at all, with the waste blowing about and washing away from the landfill sites. And it gets into rivers and it gets washed down to the ocean. And so it's not just the coastal areas that contribute to this, but it's all inland areas as well. So plastic waste in the oceans, a big problem. So what's the problem for marine life? The big bits, we've seen the photographs. Animals get entangled in them, they can suffocate, and the sharp edges can cause problems as well when they eat them. The smaller problems, different set of problems, smaller fragments, they can be mistaken for food. And so animals can starve because they're just eating plastics. But there's a bigger problem as well, that the plastic particles aren't just inert, but they can contain chemicals. And these can leach out, they can seep out of the plastics into the ocean, into the water body, but also into animals if they've been eaten. And so there's a particular set here. I've just picked out some additives, these polybrominated, polychlorinated biphenyls, both very nasty materials, highly toxic, and they accumulate. They accumulate in whatever eats them. So marine predators eat fish. Fish have these chemicals in them. And the marine predators, which live quite a long time, and so they can eat an awful lot of fish, they can pick up enormous amounts of this. And there was a story in the paper just the other day about the highest ever levels of one of these chemicals, I think it was the PBBs, in marine predators in killer whales off Scotland. And so these chemicals are getting into animals, and that's causing problems for the animals. So health problems and disrupting the reproductive ability, and they're carcinogenic. And of course, this causes us problems as well, because the fish in the sea, we eat those. Those have eaten the chemicals, they've eaten the microplastics, and then we eat the fish, and we pick up both. We eat a lot of microplastics. It's estimated that we eat about 70,000 microplastic particles per year. And they're not inert. And we really don't understand what the full consequences are from us eating microplastics. But it's probably not good. So that's a scare. And we don't know enough about it. There are people working on it, but it's probably not a good thing. William McDonough is one of the big figures in sustainability. And this is a quote that I think is very powerful, that we used to be able to throw things away. Things went away, but where is away now? Away is someone's backyard. The planet, we see that we're inhabiting a smaller and smaller planet. Away has become very close indeed. This book, Cradle to Cradle, it's a wonderful read, and he explains clearly, and not in a very depressing way, just what all of this means and how we could do things better by looking more carefully at what we do with end-of-life materials. So we've got a problem with waste. Let's look at what we use plastics for. So I've got a picture here. We've got plastics, with packaging being the biggest amount of plastic that we're using, followed by this sector here, which is building and construction. We're going to particularly look at food packaging, because the way in which we use the plastics in those two sectors is very different. Food packaging, it's transient. It may be that we're using the packaging for a very short time, few days, weeks, at the most a year or so. Most food packaging is very transient. Whereas what we put into buildings, that can hang about for a long time. Buildings last 50 years, more. The plastic just stays there. So even though we're using an awful lot of plastic there, it doesn't go round the recycling reuse loop nearly as fast. So this food packaging It goes round really quickly. It's a very big part of what we see visibly as waste. And that means that it's actually some of the thing that we should be focusing on most. So that's what we're going to do now. So what do we use packaging for? Well, we need to contain our liquids in something. We need to contain our solids in something, so particles. We need to have a container for them. And we use packaging for preventing mechanical damage, so mechanical protection for all these fragile items here. And it stops you from handling them as well, and that prevents damage. And so all in all, it's avoiding a lot of food waste. And I'll come back to that. That's an important point. What else is it for? Well, it acts as a barrier layer. And so you can isolate your food from the environment. So here we've got salad, and it's contained within an inert atmosphere, which might be nitrogen in this case. This is some fish, which is in a vacuum. So it's protected from the environment, not only by the packaging, but also, in this case, by an atmosphere which will help to preserve its life. These packets here, these are Walker's Crisps packets, and they used to have a particular barrier layer in, which made them very difficult to recycle. And so they've now changed their packaging. It doesn't act quite so well as a barrier layer, but there was quite a big fuss about that a few years ago. But potato crisps, they go off really easily and get tainted when they go off. And so the packaging there is particularly important. Cheese, I'll talk about. This is a very smelly cheese, and the packaging is helping to keep the cheese in. So what's packaging doing? It's reducing food wastage. It means that we don't need to have so much of additives in the food to help preserve it. And it means that we're able to use a global food chain. Now, that may or may not be good. It means that we're not using so much local food, perhaps, but it's what people want at the moment. And it does mean that it's possible to transport food to areas where there are production problems. So it's not all bad, but we really do have a global supply chain for a lot of our food. So here's just a table which has got some quantitative evidence about what packaging is doing to increase the lifetime of food. And if we can increase the lifetime of the food, the shelf life, then we reduce waste. So just one to pick out from that. If you look at these cucumbers here, they've got a very small amount of shrink wrap on them, a tiny amount, 0.5 gram. And the effect of that is to extend the shelf life from 3 days to about 14 days. So the cucumbers last a lot longer and there's a lot less wastage. And similar stories for these other items here. So food packaging is doing a lot to reduce food wastage. So what I want to do is a little bit of a study here, looking at the context of food packaging. And so in relation to the amount of energy, the carbon footprint that we use for making the food which is being packaged. So what I've got here is a chart, and I've got the carbon footprint of a kilogram of cheese. And so that's the energy required basically to make the cheese. And chicken, much smaller. Cheese, well, if you're a vegetarian, this may not be very good news for you. This is cow cheese, and cows actually produce a lot of methane. They've got quite a big carbon footprint. They're slow growing, and it's a very inefficient process. So actually the carbon footprint of cheese is pretty high. Chickens grow quickly, And so actually their carbon footprint is much smaller. So the carbon footprint of the food, that's that. The carbon footprint of the packaging is this tiny little red bar here. It's a very, very small fraction of the total production carbon footprint. Can't even see the packaging in these two bars, and in the disposal phase, we're not seeing the packaging at all. So packaging, it's important, but it's a very small proportion of the total carbon footprint of your packaged food. If we look at the disposal stage, then we magnify that very considerably. And what you can see is that packaging has a very small negative impact here. But if I dispose of the package by burning it, so use that as fuel, then I actually get quite a lot of the energy back. And so this is the disposal stage for packaging. If I recycle the packaging, then the impact is just this small positive amount here. We don't get any energy back. So looking at end of life, from the carbon footprint point of view, that doesn't really make sense because it's a tiny fraction of the total impact of this packaged food. However, it's not just carbon footprint that we're concerned with when we think about the impact of packaging. It may be things like the marine life. It's the problem that we've got is not just the recycling end. So there are other reasons for recycling rather than just the carbon footprint. So let's now have a look at, I seem to have managed to stop my slide sharing here. So there we go. Okay. So I'm going to look at cheese packaging and see a little bit more in detail about what the impact of this is and whether we can do things in a different way. So I'm going to do a case study on cheese packaging. And I've said cheese packaging is not just a plastic bag. So here's some cheese, it's got a package on it. It is plastic, but it's actually much more complex than you might think. So cheese it's not dead actually, it's got organisms in it. And so the cheese is maturing in the package. And what we require from the package is actually an awful lot of different functions. It's got to be a selective barrier for the molecules. It's got to let the carbon dioxide out so that the cheese can mature without the package just blowing up. But it also has to do the protecting from the environment bit. So it's letting the carbon dioxide out. It's stopping the water from getting out, because if the cheese dries up, then nobody wants to buy it. We need to stop the oxygen from getting in, so protecting from the environment, and we need to keep the smells in. So the packaging is doing all of those jobs simultaneously, which is why I say it's not just a plastic bag. So let's have a look at the structure. Here's some cheese packaging. So it's 7 layers, different polymers, very complex, less than 0.5 millimeter in thickness. It's surprisingly easy to make if you're good at that sort of thing. So you extrude all of those plastics simultaneously and turn it into a bag. So a fairly simple process for a really complex material. And these different polymers used for the cheese packaging, they're things that you may not have heard of at all, but some of them, polythene is quite a common one. So complex material, and the problem is that it's very difficult to recycle. So could we use a single polymer and make it more recyclable? So we're remembering that the packaging's got to fulfill all of these different functions simultaneously. I'm going to choose one of the functions. I'm going to choose the oxygen barrier, which is actually one of the most important things. And that's achieved using EVOH. Let's look at alternative plastics, which might be easier to recycle, and calculate the relative film thickness we would need to fulfill that function, look at the carbon footprint, and then look at the relative cost for each of those plastics. So for this oxygen barrier function, I've got EVOH, the polymer which is actually doing the job in my multi-layer film, and I've just given a value of 1 for all of these thickness, carbon footprint, and relative cost. So I've given values of 1. And then for these other plastics, I've calculated what I would need to do the same job. So look at the thickness. So for polythene, low density polythene, I need nearly 2,000 times thicker. So my original layer in that actual plastic bag was less than 0.5 millimeter. This is going to be absolutely impossible. That's far too thick. That's not a plastic bag anymore, that's a crate. PET, this is the stuff that's used to make fizzy drinks bottles. The relative thickness for that, it's 20 times what we needed for the polymer that does the job best. The carbon footprint is 22 times bigger. The cost is less, but this is the polymer that is actually closest to doing the job that the EVOH is doing. So we've done that calculation and we discover that PET is the best substitute, but it's still quite a lot worse. We're using a lot more material. And then we do the same job again. So we look at another function. We might look at the moisture barrier, do the analysis again, and see which polymer does the job for us best for that. And then again for all the other functions. And what we find is that, yes, we could use a single polymer. So we could make this film more recyclable. But there's a penalty, that the carbon footprint is much bigger because none of these polymers is as efficient as the specialist polymers that we've got. And so the thicker the carbon footprint is much bigger because we're actually just using more material. So if we're focusing just on recycling, then we use PET for this packaging. But is that actually the right thing to do? Well, it's what people are doing, actually. So they're saying, we've got a polymer film which is not recyclable. We must have it recyclable. And so we're going to use PET, but we have to use more of it. So that's the route that we're taking. And we're looking just at end of life there rather than the carbon footprint. So perhaps we should be doing things in a different way. Okay, so let's have a look more generally at what happens to polymers at end of life. So here's a chart which shows us about packaging reprocessing in the UK. And we've got that red line which tells us the recycling rate. And we've got things happening in the UK, which is the pale blue. And we've got stuff going to export, which is the dark blue. Now, you may remember that a little while ago, a few years ago, China stopped importing our waste plastic. So there's China imposing an import ban on our waste plastic. What do we see? Not a lot. We don't suddenly see all of the plastic being reprocessed in the UK. But what we do actually see is that instead of going to China, it just goes somewhere else. So it's still being exported, but it's going to other countries. Now, there was a reason why China stopped taking our waste plastic, which is that they couldn't make money from it. And so these other countries are also finding that they can't make money from it and are refusing to take our waste plastic. So things are going to have to change. We're going to have to stop exporting plastics and reprocess more of it within the UK. So let's have a look at what does happen to our polymers at end of life. So I've got a life chart here, starting off most commonly with mineral oil, petrochemicals, a bit of biofeedstock. We make our polymer. You make your product. Let's go back, not do any of that. Use the product, then you throw it away. What happens when you throw it away? All of these things are, in some sense, recycling. We're getting some value from the plastic at end of life. And I'll talk about some of these a little bit more. Landfill, going to a hole in the ground. That's not getting any use for it. And quite a lot of plastic is still going to landfill. So, the main process, the one at the top there, mechanical recycling, this is what you think of as polymer recycling. So what we do there is to take plastic, you sort it, you clean it, you shred it, you put it into this machine here, which is called an reamer, and it turns it into new plastic. And so here's the plastic being extruded, cut it up into pellets, and use those for making more product. That's what we think of as being recycling, taking plastic, end of life, and reusing it for new material, for new products. So mechanical recycling, that's basically, it's a good process because it means that we can reuse our old plastics for making new material, new products, and it reduces the amount of polymer that we need. So we don't need to make as much polymer. It saves a lot of energy. But it's difficult because the polymer, we use it, we contaminate it, and we mix it up with other things. So 100% post-consumer closed-loop recycling, which is really the ideal, that's very difficult. It can be done, and it's actually been done for quite a long time. So Ribena has been using 100% post-consumer recycled plastic for its bottles for more than a decade. And other companies are doing similar things. It costs a bit more, but it can be done. But most recycling isn't actually recycling in that sense. It involves downcycling. And so we're using the polymer for lower grade applications. And that means that we're not actually saving the amount of polymer that needs to be made because we still need it for those high grade applications. But some well-known examples of downcycling, fleeces, Patagonia fleeces made from PET bottles. The requirements for those fleeces are nothing like as stringent as they are for the bottles. So it's downcycling, but Patagonia makes a lot of money from it. And these other applications, water baths, mixing with wood, they're definitely low grade, but they mean that the polymer is being used for something, not just going for landfill. So, big question. Why are polymers so difficult to recycle? And they genuinely are difficult to recycle. The main reason, the really important reason, is that the quality of the input material is vitally important because everything that goes into the recycling stream comes out again in the recycled material. So you've got to be really, really careful about what goes into the recycling stream. And furthermore, it's very difficult to analyze polymers to know exactly what you've got in them. So you have to have a lot of faith in the people who are doing the recycling. The ideal input is a single polymer, which is clean and it's uncolored, because coloring is actually a contaminant in polymers. So single polymer, we've seen that food packaging is often mixed polymers. They can't easily be separated. Clean, well, there are some obvious things, so you're not contaminated with food, remove the metal and the paper, but there are also less obvious problems. I was talking a little bit about additives with respect to nasty chemicals, and that's a problem when you're recycling. Colouring is also a contaminant. So, consequence of all this is that applications of recycled polymers are very carefully controlled so that you don't get these nasty additives getting through into food packaging, for example. People are trying to increase the amount of recycling, and so there's a huge focus on improving the sorting and the cleaning so that we can increase the amounts of high quality polymer. So, real barriers to polymer recycling. Oil is actually comparatively cheap, and so virgin polymers are cheap. Recycled polymers are not much cheaper than virgin polymers because of all of the gathering up, the sorting, all of these processes are expensive. And at the end of all that, unless the quality of the recycled polymer is at least as good as that of the virgin polymer, then people don't want it. So processors have got to be able to sell the recycled polymer, and the real barrier at present is economics. It's not the technology, it's the economics. If you throw enough money at the technology, you can make it better. So we need to be doing that. Now, EU legislation, UK has now left the EU, but we still have legislation which is going to be put in place requiring 30% of recycled content in all UK packaging. And we've got a problem because we can't deliver that. Current UK reprocessing can only deliver about a third of that. We can't import it all from abroad because other people want their recycled polymer to meet their legislation as well. So we need to throw a lot of money at the infrastructure, collection, sorting and reprocessing in order to be able to meet that commitment. And so 250 kilotons was pledged. I bet that that has fallen behind schedule, but the UK is gradually doing something about it. It'll get there in the end, but it won't get there in time to meet its targets. So what's the situation at the moment? Very sadly, we're only effectively recycling about 2% of packaging. And that's not enough. We've got to get that higher. And so we need to be putting a lot more money into the recycling processes. How could we change the situation? We need to change the financial equations. Well, it would be very nice if the government did a bit more about that. I've been talking about policy. Now, policy is actually changing the financial equations. So if you look at this chart here, this blue picture here is the virgin PET, and this red line is food grade pellet PET. That actually got above virgin PET. That's recycled polymer, which is more desirable than virgin polymer because of the legislation. So the picture is changing slowly. If you look more generally at other plastics, good quality plastics, natural uncolored HDPE polythene, that is going up. Mixed plastics, dirty plastics are going down. So there's a push towards high-grade plastics, and we need the increased sorting, increased processing to be able to do that. So improving the technology will improve the amount of recycling. What else can we do? We can do some clever things with design for recyclability. So I've talked about narrower range of polymers. I talked about mixed polymers, so no multi-layer films. But remember here that if we do go to single polymer films, we're using more material. And so the carbon footprint goes up for that, but we're improving recyclability, so there's a penalty there. Joining methods for different plastics. If you can separate plastics at end of life, then you stand more chance of being able to recycle them. And we can get rid of colored plastics. So here are some 2-litre sparkling water bottles from Sainsbury's. They used to be green, and now they make them in clear plastic, which is much more recyclable. There are always problems here with marketers who say, oh, people won't want to buy their water in clear plastic bottles. Well, they do. Actually, people are much more compliant than the marketers would have us believe. And so we're seeing quite a lot more of these clear plastics. We don't need to use colored plastics. And so that's going to improve recyclability. There's a lot of research going on in recycling technology. And so we need to get these higher grade, higher values material, better sorting, but we can also do things with better tolerance to impurities in the mechanical recycling. Everything that goes into the recycling stream gets into the recycled plastic. If we can somehow make the impurities less dangerous, then that can improve things. And a particular example here, polyvinyl chloride, PVC, that degrades when you recycle it, when you heat it up. And we can neutralize that by using calcium carbonate chalk. There's a lot of work going on into processing of mixed plastics, and so compatibilizing them so that you can make good articles out of them. Then there's chemical recycling. So let's go back to the chart that I had. So here at the end here, we've got chemical recycling. So what's that? So it's a big process, catalytic process. We break down the polymer into essentially its small molecules, monomer parts, and reuse that for polymer production. So the arrow going back into the polymer production. Chemical recycling, it's useful for a very wide range of polymers, but it's pretty expensive. It uses a lot of energy, and at the moment, it's only being used commercially for specialist polymers. People hope that it will be possible to scale up, to use it for a wider range of polymers so that we can process these mixed plastics, difficult to recycle plastics, but that's for the future. And it's being a bit slow in coming. What else? Energy recovery. Energy recovery, that's burning. So remember that polymers are basically fuel. A lot of it comes from fossil fuel. So can we get the energy back again? Well, yes, we can. And so in London, a lot of London's waste goes down the river to this riverside facility, Belvedere, where it's burned and turned into electricity. We don't much like having energy from waste plants in the UK. We put them in places where people aren't, and we hide them. But mainland Europe has a very different attitude. So here in Denmark, Copenhagen, from the middle of Copenhagen, you can see this energy from waste plant. They're proud of it. They've turned it into an amenity. It's got a ski slope going down it. They're not hiding it away. They are proud of turning their waste into energy, and people are perfectly happy to be in close proximity to it. So energy from waste, it's not actually as bad as people think, and we can get good value from what goes into it. So, alternative packaging scenarios. Bio packaging, biopolymers, biodegradable packaging, can't we just degrade it in the same way that we degrade food? So here we've got biopolymers. Here's the marketing pitch. You grow things. You make your polymer, you make your stuff out of the polymer, and at the end of life, it goes back to making new plants. We don't have any of this fossil fuel, and we don't have landfill problems. It's not quite like that. Biopolymers, they're a very small part of the polymer market. It's only about 1 to 2%. So we're looking at a really small amount here. And there's also a lot of inaccuracy around about what biopolymers are. So the common ones are made from maize, sugar, softwood. And there's a common confusion. People think that biopolymers are biodegradable, and so you can dispose of them by composting, but in fact, only about 25% of them are. So this composting, that's what people are thinking of when they're talking about biopolymers. Actually, most of them aren't. Composting, you do produce something which is then used for making new plants. But we've got a problem with biopolymers. So they're more expensive. They are resource intensive to grow. And so this is industrial scale farming. It uses a lot of fossil fuels and pesticides. Making the polymers is resource intensive. And there's actually not enough biopolymer around. 1 to 2%, the market is growing, but we haven't got enough feedstock to make enough polymer to meet our demand. Problem as well, the polymers that do biodegrade, they require commercial facilities, so they don't mostly degrade in the natural environment. And so waste, they just contribute to the waste in the environment. And the commercial facilities, they generally reject plastics because biopolymers, they can't tell from other plastics. And so polymer waste of all sorts tends to end up in landfill unless it can be well identified. So they tend to just reject all these biodegradable plastics. So they're not getting to the composting facilities. So this is a bit aspirational. Bio-based polymers are going to be important, and the use is increasing. And this aim to eliminate production of polymers from petrochemicals is a very worthy one, but we're not there yet. We need to have more bio-based feedstock, and there's active research into improving their biodegradability. So, what about cardboard and paper? Cardboard and paper, they must be good, they're natural, not quite like that as well. Again, the carbon footprint of cardboard and paper is higher than it is for plastics. So this was a little company in Devon which did a research study with their local university. They wanted to reduce their carbon footprint, but what they found is that paper and card have got a bigger environmental impact than plastic. And that was very sad. Their customers didn't like it at all because their customers wanted them to be using paper bags and cardboard boxes, and actually the environmental consequences of that were bad. So what the company did was to recognize that single-use disposable packaging is bad, and so to transition to reusable but plastic packaging. So what should we be doing? We're getting onto the solutions here. Reduce the number of articles. Yep, we need to do that. So anything unnecessary, we just don't use. reduce the amount of material, thinner walled containers. That's problematic. We've shown that if we try to make something which is recyclable, then actually we need to use more material. What about reuse? Reduce, eliminate any single-use items, and don't just replace them with non-plastics, because actually the environmental consequences of those are bad as well. Let's just have a quick look at reuse of packaging. So individual water bottles, cups, that's good. Requires a bit of effort from people, but you can do it. And the hygienic consequences, you are responsible for washing your own containers. With commercial reuse, it's a little bit more problematic because you've got to be able to guarantee that those containers have been cleaned. And there's got to be standardization. So traditional glass milk bottles, there was a reverse logistics supply chain. You could get them back again. They were washed and redistributed. And so that was a closed loop. Deposit return schemes may get back to that sort of state, but it's not easy. And it takes a lot of effort and people working together to make that happen. So it could be done, but reintroduction does require a lot of cooperation between different companies. And there's also a problem that the reusable containers, they're more robust. And so you need multiple reuse before you've got eco-efficiency. So there's a problem there, and I'll talk about that in just a mo. So we're trying to improve the recyclability of products, but we also need to make sure that we actually gather in plastics into the recycling waste stream. So we've got a problem there that you don't know what you should do with your plastics, because everywhere you go, the regulations are different. So in Cambridge, we've got different regulations at home and in the workplace. The instructions for what to do with our plastics are different in those places because different companies have different waste management facilities. And so they need to have different regulations for what they take into the waste stream. So it's really difficult for people to do the right thing. And one of the things that the UK is trying to do is to put uniform regulations in place across the UK. That will take time. So what about knee-jerk reactions? Getting rid of plastic packaging. In Bangladesh, they had a problem with plastics blocking rivers. They introduced a plastic bag ban, and that's been followed by other countries. So here in India, this is the sort of problem they have with plastics in the streets. They put in a ban on single-use plastics with huge fines and intended to roll it out over other bits of India. But it didn't work. It didn't work because it wasn't enforceable. There were no alternatives in place. And so actually that went away and they're trying other things. So it was laudable, it was just too fierce, and it hadn't been properly thought through. Just thinking about the plastic bag ban, I was talking about the environmental footprint of things and the need for reuse. So let's just take a quick look at how many times do I have to reuse my shopping bag to be green? I'm going to look at carbon footprint, but just to remember that there are other environmental impacts as well, which may be from pollution or water consumption. So a quick whiz through here. Take a Sainsbury's thin single-use bag, but at least use it as a bin liner at end of life. Heavy duty bag, one of these bags for life, you need to use 4 times. Polypropylene, a bit more robust, 11 times. Paper, got to use it 3 times. the cotton bag that everybody wants you to use. You've got to use that 131 times, unless it's organic cotton, in which case you've got to use it 400 times because the production of organic cotton is much less efficient. And that's if we're looking at the carbon footprint. If you look at water consumption, you need to use it 7,000 times. So the unpalatable conclusion that we've got here is that this single-use bag is actually more efficient in environmental terms, the least carbon footprint, than any of these alternatives. We've got to use them too many times for it actually to be efficient. People are looking at alternative materials for food packaging, and here's an idea. So something that doesn't look like plastic, which will degrade in the same way and is a waste material. So making food packaging from a natural waste material. Are we going to be able to get the volumes up? Maybe not, but that's the sort of way that people are thinking. So, conclusions, what should we be doing? We need to recognize that plastics are actually pretty important. We shouldn't be just getting rid of plastics. We need to be very careful about knee-jerk reactions. We need to think about the whole system, about the contribution of packaging to the food which it's also packaging. So look about the whole system there. It reduces food wastage, so it really isn't all bad. Food packaging is pretty important. If you replace it with other materials, the environmental impact is generally higher. Plastic is the most efficient material. We've got to do something about end of life, but packaging from plastic is really efficient. Bio-based, biodegradable polymers, there's a lot of good stuff, but actually you need to ask questions. We need to get them to degrade in the natural environment, and we need to make more of them. There's a lot going on with alternative materials and design for recyclability. We definitely need to stop using unnecessary plastics, and we definitely need to have no single-use anything, not just plastics, but anything, no single use. We'll be looking at more energy from waste. We'll be getting some of the value back from plastics, and we've got to get more recycling. So got to increase the recycling capacity and make it really easy for people to recycle, to do the right thing. So that's the end. I'm going to stop sharing now and go back to Marcus. Hello.
Thank you very much, Claire. Huge thanks to you for really sort of such an insightful and thought-provoking talk. I've got a few questions here come from people watching, questions people have put in through the Isaac Physics website. One of them is this: do you think there will come a time when the price of oil means that virgin polymers can become more expensive than recycled polymers?
Yes, that's a very important point. If the price of oil does go up, which it will do, then the whole situation changes and polymers are going to be seen as a valuable material. So the recycle, that will be a real boost to the recycling, that end-of-life polymers, people will want them and they will throw more money into the processing aspects. So yes, that will change the situation.
Thank you. Yeah, I'm aware we've reaching 6 o'clock, so it's the kind of time that the lecture is due to finish, but we have got time to actually to go.
Apologies for overrunning.
we can keep going, that's fine. So another question here I've got from Nina. She says, I'm a little confused why the wrapper from the beginning is made from potato starch. Is still plastic if it's made from bio-based feedstock. Would you be able to explain this? Thank you.
Yes. Okay. People don't want to think of plastic as being something which is bio-based. So they're using plastic for as a bad word for things which come from petrochemicals. So if something comes from petrochemicals, it's plastic, it's bad. But those wrappers were made from bio-based polymers, but they're still plastics. They've actually got the same properties as the petrochemical-based plastics, but they come from a bio source. So it's really terminology. Plastics is a bad word. I don't want plastic in my wrapper here. Therefore, this one, which is bio-based polymers, I'm not going to call that plastic. I don't know what I am going to call it, but I'm not going to call it plastic. All right.
Yeah, people get very upset about the wording there, don't they? That's just it has a big effect on marketing, I guess, as well. Yeah.
It absolutely does. Yes. Yes.
Other question, what have we got here from there's an anonymous question here, but can't we make use of technology to create items to store the food, preventing us from wasting the plastic used to store the food? So I think it's looking at, are there any advances in technology can you foresee that would still have the same function as the plastic food wrappering, but actually perhaps something that
Yeah.
less smaller carbon footprint.
Yes. I mean, I think that in many cases, we still need some sort of a container to keep the food away from the environment. So if we don't use plastic, we'll be using some other kind of material. I mean, I think one of the things to think about here is, can we use something which is reusable rather than the sorts of packaging which we're most commonly used to now? So can we use more boxes which can be washed again and reused rather than thrown away?
Great. Well, once again, thank you for a really insightful talk. Really much appreciated you broadcasting this and coming and pitching it really well as for sixth form, A level students thinking about going into material science and engineering. So hopefully it has inspired some people to do that. Now, just a few details of there's a Cambridge Physics Centre talks that are coming up. Okay, do take a look at the Isaac Physics website and the Cambridge Physics Centre website. Next talk is on the 9th of February, and there's a talk, Ripples from the Dark Side of the Universe. Professor James Howe, Emeritus Kelvin Professor of Natural Philosophy from the University of Glasgow. He's going to come and talk. And